All right. So I thought it would be easier to record the demo for HEP tables than it would be to present it at real time, partly because we're a little stressed for time in this parallel session. And partly because there are parts of the demo where it will take a minute or two to complete and one can skip forward. So this HEP tables, the way I thought I'd do this, I start with a brief introduction of what it is, and then do the demo. This demo will involve both the HEP tables work, but also the ServiceX front end work and ServiceX itself, which for this demo is, I'm in Seattle and it's running on a Kubernetes cluster in Chicago at the University of Chicago on the River cluster. So it's a reasonably complete end-to-end demo. So by way of introduction, I think maybe I will just start with some slides. I'm going to do very high level. I'm not going to do a detailed description. Let's see. So the COFIA folks asked me to come and talk a little bit about HEP tables, and so I'm pulling a couple of slides from this talk. So the most basic overview is this slide here. So here's the basic idea. The person sits at the computer and builds a query or runs a Python file that contains a query, or it doesn't actually even have to be Python as long as the lower level is in the proper format. It communicates with some packages, which I collectively called HEP tables. HEP tables will make use of things like awkward, as it does currently, and eventually, although not yet, COFI. And it will take parts of that query that ServiceX can serve, translate it into an intermediate language called Castle, send it to ServiceX. ServiceX will then pull the actual data from a data lake. For this purposes of this demo, the files being pulled from the data lake are a data set, an Atlas XAOD data set produced by the production, the production system in Atlas, but they could be any data set that ServiceX can deal with. So at a very high level, what happens is when the person enters their query, a DAG gets built, a computational graph. So this is an extremely simple one, which just looks at the electron PT from some data set. That's what the XAOD table represents. And it takes that PT and divides it by 1,000. This is because Atlas, for whatever reason, historical reason, has chosen to store everything in units of MeV, and my brain works in GeV. So first thing I have to do is divide everything by 1,000. So this is an extremely simple computational graph. It will involve pushing down to ServiceX to get all of the data and bringing it back up and displaying a plot of electron PT on the user's system. So this is what HEP tables job is. Now, what about a more complicated query? Let's say we have a query that ServiceX can't do. So ServiceX is designed to do only the simple things, extract data, make simple cuts, things like that. Let's say we want to do something with multiple objects. So then we need to layer something on top of this. So HEP tables job is to take this DAG and translate it into something ServiceX can do. We can put something in front of that above HEP tables, just another box, and its job will be to examine the DAG, figure out which parts ServiceX can render, get those done, and then use something else like awkward and COFI to put it together. So I have an example towards the end of this talk, so I'm going through, here we are. So let's say this is our complicated DAG, which does lots of operations. ServiceX, however, can only do the ones that are circled. In that case, we would want to call on ServiceX to do those, and then we want something else to take the results of the ServiceX and then combine them up the tree until we got back to node number 1. This is a job of something called HL tables for high level, because I was just trying to get it done. I didn't think much about the name. Okay, so this is the system that I'm demoing, that I'm talking about. All right, so we can, whoops, sorry. So what we can do, so there's some hep tables documentation. So let's start this up. So the very first thing I'm going to do is I'm going to run the demo. It's going to be using cache data. And the reason for doing this is because when it goes out to ServiceX, each query to ServiceX takes of order 1 to 2 minutes, depending upon ServiceX and networking. And rather than make you sit here and watch for a couple of minutes, I'll first do it with the cache. And then the second thing I'll do, well, that's not hopeful. The second thing I'll do is do it with ServiceX actually running in the background. Okay, so the physics plot that we want to make is I want to get a look at events, and in each event in the Monte Carlo, there are 2 long-lived particles. I want to look at their lifetimes. And then once I've looked at their lifetimes, I want to ask if the spot that they decay is within 2 different detectors, a calorimeter for one of them and the muon spectrometer for the other. So effectively, I want to ask the Monte Carlo truth, how often do you have one of these 2 particles, an event where one particle decays in the muon spectrometer in Atlas, and the other one decays in the calorimeter. This is strictly a Monte Carlo test. All right, so of course, the very first thing we have to do is load up the boilerplate. So you can see here, this first line, ignore it. This is just because I haven't made everything official packages yet. There's the standard plotting I need to import. Now here comes more interesting things here from HL tables, hep tables, and the event data set. So we'll get to that in a moment. Second thing I need to do, okay, let's restart this. I'm a little worried now. Let me restart and clear all. I thought I'd started from a clean kernel, but it looks like that may not have been the case. Okay, that's much better. It takes a little while. Okay, so I need to load up the data set names, and we're going to use this huge data set, which is a long-lived particle data set from Atlas. It exists on the grid, and it's in the form of X AODs, and that's just strictly its data set name. There's some metadata associated with it, which is not important right now. So the very first thing I've got to do there is create the actual base of the DAG. So this DF is now the one of the the leaves. So the very first thing to do there, once I've got the basic data set, is to get the truth particles. This is an official XAOD bank called truth particles, and I only want to look at truth particles whose particle ID is 35. So that's what I'm doing here. You'll notice that this executes instantly. Nothing actually happened when I ran that. Instead, it's just building the DAG at this point. Now, what I want to do here is make a histogram of the truth. So I'm going to count the number of particles in each event. So that count applies just to each event, and render it. If all goes well, I should be getting a histogram which only has 2 in it. So there, what you saw was that green bar indicated that it was loading the data. Now, in one case, it might go to ServiceX, in which case you would have seen it move much more slowly. But in this case, since the data is already on my machine, it went quite quickly and loaded up all of the data, and then put it in a histogram on which I applied a couple of matplotlib commands to, and you can see it's just 2, which is exactly what we expect. Okay, now it turns out a funny feature in Atlas data is that a long-lived particle which decays may not always decay. And the reason it won't decay is because if its lifetime is so long, it's well outside the detector, the Monte Carlo doesn't bother with doing the decay because that will be extra work and wasted CPU time trying to simulate a particle which has already left the world volume in JM4. So we have to protect against that because later on, we're going to want to know the decay length, which means subtracting the position of the production from the decay vertex. And if we try to do that for something that doesn't have a decay vertex, we'll get into trouble. Okay, so now we're going to make the same plot just to look to see how big a deal that was. And you can see here, this is a log scale. One event of almost the 300,000 is missing a decay vertex. I just happen to know it's a decay and not the production vertex because of work that I did previously. Okay, so the real thing we want to know about is the decay. So what we're going to do is these are both effectively 3 vectors, the production vertex and the decay vertex. So we're going to create a 3-vector. So this is shorthand for building up some 3-vector operations. It's just a Python object, which then when you do the subtraction, understands what to do. And furthermore, when you do the .xy, understands how to calculate the transverse that I just called xy for the transverse. And of course, we're in millimeters, but we want to think in meters, so we divide by 1,000. Note again, that was just building the DAG, so that was instantaneous. And now we can make a histogram of this. So in this particular case, we have to get the x and y position of the decay and the product. So that's going to end up being 4 queries. And then once that's done, you can see we got an exponentially falling distribution, sort of the reverse of COVID-19, exactly as you would expect for a standard particle with a constant proper lifetime. Okay, so ignore this. This is not so important. These are just plots from some previous work for comparison and setting. I need now to create a detector object, and I just did this to simplify my life. Basically, I want to be able to draw boxes on slides, on plots. That's what the draw LXY box is. That will become self-explanatory in a second. And the second thing, which is more interesting, is I need a test which will say, given an LXY, tell me if I'm inside this, whatever detector this represents. So the calorimeter here or the muon there. Okay, so now what I'm going to do here is I'm going to plot LXY and do it for both the calorimeter and the muon. So I'm going to make the same plot as before, but I'm going to put the boxes on. So you see the boxes right here. I'll put the boxes on for the calorimeter and the muon. So note that that didn't even show any updates. That's because the system was smart enough to realize it already had this exact data in memory, and it didn't even need to go to the local disk cache to fetch the data out. Okay, great. So now comes the really interesting part. So this tells this, you can look at this and you can see the size, approximate size of the calorimeter and approximate size of the muon sensitivity. And so the next thing we want to do is we want to know, we want to count how many events have at least one particle, one decay in the muon detector, one decay in the muon, in the calorimeter, 2 in the muon, 2 in the calorimeter, and 1 in the calorimeter of the muon. So you'll notice if you look at this code carefully, we have to count, and then we have the LXY squared, which is here. This is us making sure that we're only looking at events with 2. And that's because, notice I have to look at the first one and the second one. So here for 1 muon, I say, I have an or here, right? So it's either the first or the second. Same for the calorimeter, first to the second. Now if I want 2 muons, it's basically the same, except for an and here for the calorimeter. Of course, for 1 in each, it gets a little more complicated because we have to do the symmetric operation. So it's 0 and 1, so cal inside or and muon inside, or muon inside and cal inside, so we reverse them. And so now here are the numbers, and this was basically what I wanted. Okay, so let's now boot up ServiceX, delete the cache, and then we can watch that run, and I can mention a couple of more things while that is running. Okay, so the very first thing I need to do is delete the cache. So for that, we are going to need a terminal window here. Okay, now the question is can I remember where the cache is? Delete Oh, I'm sorry about the color. Users. Isn't it nice that Windows chose that name? Don't anybody call me that. Let's see. Temp. Nope. Local temp ServiceX. I don't want to delete that yet. I want to first make sure I've got the right thing. Apologies. Yes, okay, so there it is storing those, for those of you who know ServiceX, you'll recognize those as request IDs, and inside each one of those, for example, 32, you can see there's a whole bunch of root files that it pulled back. They could also be arrow files or Parquet files, rather. Those could also be the things that it come back. There are a couple of formats. This particular system happens to be configured to use root. Okay, so we do want to delete this. Let's see, yes, let me, okay, great. And now if I do a directory, I should get, doesn't exist. Okay, perfect. Now, the next thing that we need to do is, for currently to run ServiceX, we need an open port. Two ports have to be opened. So eventually this restriction will be removed when we hit 1.0, but for now. So we need the port which runs the, it's the app communication. And then I need a second port which will run, 9,000. Access to the object store, which is where the root files are going to come from. And then I think it would be also fun to have available a, whoops, that was not what I wanted to do, sorry. Terminal. It would also be fun to have, can I make a third? Wow, I can. Something where we can sort of see what's going on. Whoops, I have to point it. Yeah, so there you can see the pods that are going on. And this will become interesting a little later on when we start, when we run lots of jobs. Okay, so now here, let's go back to, I'm going to just do run all cells so it starts running and then we'll keep up. Hopefully this is going to work. Okay, so it started, and now here you can see, I'm sorry, the data set size is so long so you can't see that this is running. But you can see it's now starting to make some requests up here into ServiceX, and these periodic requests are basically it requesting status. So it takes it 15 to 30 seconds or so. You can see here that's at 10 seconds, then 15 seconds. So we'll watch this one as it comes back. And here, if we go look at the pods, you can now see 20 transformer pods all up and running. And very soon they ought to start delivering results. It's about the right time for results to start coming back. He says with fingers crossed. Okay, here, so you can see a couple of connections were made and files were pulled from the database as the system finished off. So here are 10. There are some stragglers. There are some files which take a little longer than the rest for reasons I don't fully understand. But nonetheless, this is pretty quick overall. The upper line here would be a similar progress bar. And it's just the number of processed, and it differs, the two differ when you're downloading a lot of data or you're on a very poor connection and it takes a while for the data to get there. That's why there are two progress bars associated with a single request. All right, we're almost done. We're missing one file. There we go. And now the plot was made, and of course it went on, and it now, the request to ServiceX is a little different because we're now gating the request on the prod vertex and decay vertex, which means it had to go back out. And you can see the old request, the pods are retiring, and the new request is already up and running. Okay, So I want to let this go until it starts to run this histogram file 2 down, because there's just one last point I want to make, and it's kind of a bit of a point of pride, both I hope for the people who have really done the underpinnings of ServiceX, and also for me being able to orchestrate this. So just let's give this another minute, and then I will talk about some issues that I have with this current system. 2 in particular. All right, so we got 10 of the 15 files. Of course, hopefully you just fast forwarded through this part of the video. All right, there we go. Same plot as before. Now note that, remember this required 4 queries, the X and Y for the decay, and the same for the production. And note that all 3 have been issued at once. And in fact, if we go over now and look at the number of pods, it's a little bit, so there's the retiring, the previous request that's being retired. But look at all of these pods that are up and running and servicing. So this is the beauty about the scalability of something like ServiceX. And the result is, while each one of these is going to take, what, about 1 minute and 20 seconds or so to run through this grid data set, it's going to take it about 1 minute and 20 seconds to run through all 4 of these data sets. If you're trying to think about what's the equivalent amount of work here, it's as if you submitted a grid job, waited for the grid job to run and finish, and then used Ruscio to download the resulting files. That's approximately equivalent to what's going on here. There's no reason you couldn't run the transformer by hand and get this similarly, but of course you'd be responsible for all the scaling, and it's not the way most people usually run. Now, while this is completing, which will actually be quite quick, there are a couple of more things I wanted to point out. So one is getting a single query is ridiculously fast. Imagine that this was something you wanted to do a lot. This is why caching is put in here, is because I'm not sure about most people, but I certainly find myself restarting Jupyter notebooks pretty consistently, and having to wait a minute and a half or a couple of minutes to get down to the bottom of a Jupyter notebook would be basically unacceptable. Okay, so that's now finished. Whoops. Sorry about that. Lost my cursor. Here we go. So that's now finished, and you can see now all the rest of the plots did not require queries, so we've gone all the way down to the bottom. Okay, so now the next thing is if you think a little bit more carefully, and many of you may already have, about this particular query, you'll realize we're running over a single data set, and we could have pulled all 4 values at once. There's no need to have spawned 4 of these jobs. That's completely correct, and the system is not currently smart enough to recognize that that is the case. But that is something that certainly need to be added, because otherwise this is frankly a waste of resources. Another thing to think about along these same lines is, for investigation, what I'm doing right now works quite well. But now let's say we know what we want to do, and that table at the end is what I want, but now I want to do it for 50 different data sets, which is actually correct. That is my next step. I need to be able to do this for 50 different data sets. And I want it to happen, as fast. Clearly, 1 job per 50 data sets is the right way to go, right? But if I need to make these other plots at the same time, all of this should be combined into a single run over the file. Getting the data into ServiceX is by far the most expensive thing. Actually running on the data is very quick. So something, and I'm not sure exactly what needs to be done there. The current way we do this is we build a large n-tuple maker, which brings out every possible leaf that we want. We know which leaves we want. It should be possible to build a coherent program which can figure that out and do this on its own. We're obviously extremely close just in this Jupyter notebook. Okay, there's one last thing that I wanted to point out. So when you go down to here, if I run this line, let's put a % time in here to time it. Okay, maybe you can hear it. The fan just went on my computer. That took 5 seconds. All of that time was spent in the CPU. I have one of these new Zen 2 AMD Ryzen processors. I think I've got something like 24 or 12 cores with hyper threading, so 24 logical threads of execution. And if you go look at my CPU during that 5 seconds, only a single one was used. And there are two reasons that that's going on. One is, let's just look at a single expression. In this particular expression, a couple of things are being calculated locally, like these if statements, basically, this mask. This is generating a mask. That's being calculated locally, and it could almost certainly be done in 2 threads and then combined. That would speed it up. The second thing that's being done is each one of these statements here is being done one at a time. This is all sequential rather than in parallel. So look how easy it was for me to build up a sequential set of statements which use the computer in a rather inefficient way. So the question is, the nice thing about this is that you can read this count and you can basically understand what it's doing, and it's a single line. If I had to do this the imperative way, I would have a loop, and then I would start accumulating for each one of these, each particular situation. And then in the end, I would get a set of numbers and I would print them out. So the logic would be spread out everywhere. This is declarative. It's building a DAG. And the logic is all there in one line. So somehow we have to combine the convenience of doing multiple statements at once in parallel so that we can take advantage of the many cores of my computer or eventually an analysis facility, and also render here. Let's see. There was one more. Oh, yes. The other issue, and this is a much more generic issue, is take a look carefully at this statement. So I glossed over this previously on purpose, but here I want to test whether or not I'm inside the calorimeter, if the first long-lived particle, Monte Carlo truth particle, is inside calorimeter, or the second one is inside, right? So the OR statement, I think we can all agree, it's not the official OR from Python, but due to Python semantics, you have to use that OR. I think most of us will look at that and immediately understand what it means. The cal.inside, I wrote that object up there. As somebody who knows this code, I'm pretty sure I totally understand what cal.inside means, and that's pretty straightforward. That's not opaque. This S0 and S1, so if I know ahead of time that S0 and S1 are Monte Carlo, if S represents the Monte Carlo particles, maybe I could have chosen something better than S. S0 and S1, it totally makes sense that it's 0 and 1. But this here, having to do map sequence here, so this was me doing something quick and dirty, but the problem is that LXY_2 is actually 2-dimensional. It's got one row for every single event, and then it's got 2 numbers. It's got 2 sets of numbers, or 2 numbers in this case, an LXY for particle 1 and LXY particle 2. So it's basically a 2D array. It's represented as a jagged array, by the way, but it's basically a 2D array. And I need to get at the second and make tests on the second index. Normally, we would write this with a slicing expression with, say, a colon or just a comma for the first one, and then the second one. So we do open bracket colon 0 colon comma 0 and close bracket, then open bracket colon comma 1 close bracket. I steered away from that because to me that is a fairly opaque way of expressing what I want, but nonetheless somehow I have to get to the point where I have an array for each event. So this map sequence is now turning this into something that goes over per event. This is also something that is not does not work, I think, too well with the current system. But this, instead of being the underlying mechanics, is something to do with HEP tables and its ability to express. All right, that is everything I've got for this demo, and feel free to ask questions or send email. Thank you very much.